All right. Yeah, last time talking about the computational complexity of the binary search. That's not fair, man. The robot only has computation time. I gotta type the stuff out. No, wait. No, the robot only works once a month. So the fact that it's beating you is not good. Yeah. All right. So we've gone over the idea of the binary search, and it's because every time when I look at the 8, I'm allowed to say, okay, is it less than or greater than the 8? If it's less than, I go over here, thereby eliminating all values in my collection that are greater than 8, which if we're lucky is about half of them, which is fantastic. Where if we do a linear search, we got to go 1, okay, next. We're not using the advantage of the fact that the information we're looking at is ordered in some way. But you'll notice the key to this is the information we have has to be ordered. It has to be the case where I say 8. Is the number bigger or less than 8? If it is bigger, then I know which side it must be on. If this is not an ordered collection, if this is just some random collection of numbers and they have no order, then I can't do this strategy. So this awesome strategy of eliminating half the stuff requires the information that we have is ordered in some way that we can make these types of decisions, which is really interesting, but it's an important requirement. So you might say, oh, great, binary search is fantastic. Linear search sucks. Yeah, but linear search always works. Linear search works whether this is in order or not. Binary search, the data has to be ordered. So, computational complexity. Where do I hit that? Iterative, for now. Okay, I guess I don't have a subsection for it. So, okay, we get away with looking at fewer things because we are ignoring half the remaining elements every time we continue our search. Any idea what the relationship between the maximum number of checks and the number of elements in our haystack n? So, the question I have is, following this shape, how many things are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There are 15 elements here. So, what's the relationship between like the height of this like this structure here and the number of elements in there? Well, the relationship is, well, the number of nodes is going to be equal to 2 to the power of h plus 1 minus 1, where h is the height of the tree, or in this case, the number of steps needed to take to get from the top to the bottom. So 8, 12, 10, 4. So let's see if we can plug that in. 4. So 2 to the power of 4 is 2, 4, 8, 16. Oh, 2 to the power of 4. Hold on. Number of steps needed to go from... Oh, I think we count this as 0, 1, 2, 3. So this is level 1. 1, 2, 3. So the height of this is 3. So we do 3 plus 1, that's 4. 2 to the 4 is 2 times 2 is 4. 2 times 1 is 1. 2 times 2 is 4. 2 times 3 is 8. 2 times 4 is 16. And then we've got our minus 1. That's how we get our 15. Or we can flip it and just isolate for h. Well, in that case, the relationship is the height of the tree is log base 2 of n plus 1 minus 1. So n here was 15. 15 plus 1 is 16. Log base 2 of 16. Well, that's 4. Minus 1 is 3. Okay? So we would say, because here's the thing. When doing this search through this data, this binary search, I go, is the number I'm looking for 8? If it is 8, I'm done. If it's not, I say, okay, greater than or less than. So let's say it's greater than. So then I say, is the number I'm looking, is 12? Is that what I'm looking for? Yes or no? If it is, great, we're done. Otherwise, keep going. And the worst case scenario is we have to go all the way down the tree to one of these little like leaves here, we call these things. If I go, okay, is it 8? Is it 12? Is it 10? Is it 11? Let's say it was 11, or it was 11.5 and it's not there. Either way, the worst case scenario, I have to ask like 1, 2, 3, 4 questions. So the computational complexity, the amount of work required in the worst case scenario is how far do I have to travel down this tree in the worst case scenario. And if it wasn't obvious, we call these things trees. It's just turn it upside down and that makes perfect sense. Where here, worst case scenario is I got to look at all of them. Right? 1, 2, 3, and keep going. Here, I don't need to look at all of them. I only need to look at each of the things as we work our way down the tree. Because if, let's say I'm looking for 9, 8. Well, 9 must be to the right of 8. It must be to the left of 12. It must be to the left of 10. And if it's there, great. If it's not, well, it must not be there. Because, well, 9 can't be on the other side of 8. Right? And if there's nothing to the left of 10, well, we're stuck. So what's really interesting about this strategy is how many steps do we have to take? And the answer is, well, it's on the order of log base 2 of n. Uh-oh, there's a bug. Someone can go fix this. Here's an easy PR. We're missing a bracket or a parenthesis here. Look at that. Someone go make a PR real quick. Whoever's first gets it. So we've gotten ahead of ourselves. The above explanation uses details we have not discussed. So if you're scratching your head, you're going to say, what? That's fine. If what I explained kind of made sense, at least intuitively, fine. But if you're freaking out, don't worry. Don't worry, that's normal. So, we can make a generic implementation of a binary search using an iterative strategy. And here's the iterative one. We start with a low index, 0, a midpoint index, a high point index, which is the height, or like the length, of the haystack, and the midpoint, which is somewhere between the two. Then I say, well, the low index is less than the greater index. This should be a lot of the time. If the information we're looking for at the midpoint is equal, then we return the midpoint. We're done. If we need to look at the low side, if the thing we're looking for is actually less than the midpoint, well, then we now say, well, the high point is now the midpoint, -1, because we don't need to consider the midpoint anymore. Meaning, if I have this, basically, when this starts, we would be, low point is 0, which has the value 1 in it. The high point is 14, I guess, which has the value 15 in it. If I look at the value here and say, oh, okay, well, this is the midpoint, and if the number is less than 8, well, then I can say, well, redo this, but just say like the high point now is the 8, because I now know it's got to be like less than this 8. In fact, I can say the 8 minus 1 for whatever index that would be, so that would be 7, 6, right? So if it's on the low half, we'll then update the high end to be the middle point. -1. If it's in the high end, if the thing we're looking for is actually bigger than the midpoint, well then now the low end is the midpoint +1. And if we ever get the case, because see how we're like moving the lower point to be midpoint, so this lower point grows bigger and bigger, and high point, all it can do is get smaller and smaller. If they ever cross each other, where low point is not less than high point anymore, we return -1. Don't get me wrong, this is a beefy algorithm. If you look at this and you immediately think, what? I will say it's a simple algorithm. There's not a lot of complex stuff going or complicated stuff going on here, but it's definitely not trivial. There's definitely some head scratching. And I would urge you to, look at this and play around with it with a sheet of paper and a pencil to make sure it makes sense, because binary search is a very important algorithm. So this is the iterative one. We know that because, well, I see a loop and go, okay, great. But here's the thing. Here's the recursive one. Wouldn't you get 0.05s for the midpoint, or does that matter? Huh? Oh, like 0.5s. I was thinking that meant second. Well, you could, but then just do integer arithmetic and just always round down. So like integer division. So if it's, just deal with integers because the indices are integers. You can't have a float index. So just, yeah, just do the, if it's 17 and you divide it by 2, well, that you'll get 8. Because it's 8.5, but well, you round down to 8. Right? Yeah. Does that answer your question? Yeah, cool. So, awesome. Bilbo's got the pull request, so there we go. So here is the iterative one. You know, there's a lot going on, but let's have a look at the recursive one. And your first thought might be like, whoa, what the hell? What's going on here? Well, no, here's what we do. If the low point is ever bigger than or equal to the high point, return -1. That's the base case of we didn't find it. Find the midpoint, which is going to be this right here. The midpoint calculation. You can't just do high point divided by 2 because the low point might not be 0. Because like, what if the low point's 10 and the high point is 20? Well, here you would do 20 minus 10 divided by 2. Well, that's 5. But then we have to do 5 plus the low point to get 15. And 15 would be the midpoint between 10 and 20. Right? So this is just calculate the midpoint. Oh, let's actually start by saying, what do we get? Parameters. The needle, the haystack, the low index, and the high index. That's all this function takes. Base case of we never found it. Calculate the midpoint. If the thing we're looking at the midpoint is what we're looking for, well, that's the other base case of, well, we're done. Return the midpoint. We found it. Otherwise, if it's less than that, do another binary search on the left side. Yeah. Do another binary, just do a binary search again, but on that half. If it's greater, do a binary search on the right half. And let's go back and look at the image, right? Look. This is a recursive this is a recursive thing visually. This grows by 2, this grows by 2, this grows by 2, this. If I do a binary search starting with the 8 and conclude it's on the left side, great. All I have to do is, just do a binary search on the 4. And it's going to follow the exact same pattern. It's still this binary, this tree structure. So 8, is it the thing we're looking for? Yes or no? If it is, we're done. If it's not, and it's less than, just do a binary search on the remaining bit right here, on this half. And this is an example of where I think, I don't know, sure, this code is complex. Sure, this code isn't trivial, but it's understandable. And this code doesn't necessarily look a lot cleaner, but to me, the recursive thought, the recursive mentality, the recursive approach to understanding binary search is so much more accessible to me. To me, I find it so much more natural. Do a binary search on the whole thing, starting at the top. If it's what we're looking for, great. If it's on the left-hand side of what we're looking at, well, just do the exact same thing again, but on this sub-problem, which is the left half of the tree. Or the right half of the tree if it's bigger. That's it. That's all I gotta do. Think recursively. This is the lazy person's approach. Did I find it? Yes. Or, am I done? No. Did I find it? I don't know. Otherwise, just do it again. How do you do it again? Don't think about it. Just the base cases take care of that. So see how if I do a binary search on this, and then I do a binary search on this whole thing, let me make sure I'm making it clear which thing we're doing the binary search on. If the first time I'm doing a binary search is on everything, well, then I'm analyzing everything, okay? But then the next time I do the binary search, I'm only focusing on this part. Then the next time I do the binary search, let's say I'm looking for 5 or something, I only need to focus on this part. Then the next time, I only need to focus on this part. And well, I'm done because I found it. But see how like, these are all like sub-triangles until we get down to a single value. And here's the thing, I could grow this again. Nope. Remember, this pattern is now like, obviously this is not going to be an ordered binary search tree anymore. Ignore the numbers here. But I could keep doing this and grow this forever and ever and ever and ever and ever. And then we have another thing. See how like this, it's the exact same pattern over and over and over again. I can grow this forever. I just double it every time. Do we see, can you see the pattern I'm trying to show you here? Let's zoom out and do it again. And then here's another one. See? It's the same thing. So if I want to do a binary search on this, so I do it on the whole thing, and then the sub one, 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 so on and so on and so on. Isn't that cool? I think that's cool. This is where it's I don't know, to me, this is where computer science starts to get like, whoa, yeah, that is pretty neat. Maybe it's just me. But does that make sense? Like you're being awfully quiet. So I'm hoping you're all following reasonably well at least. Yeah, I think it's neat. All right, yeah. Recursive, okay, great, cool. Great. All right, time for trees. Okay, well, trees are a generalization of any linear structure. Think of the bag, the indexed bag, or the sorted bag, or just a bag. A bag is this like linear collection. And a tree is a generalization of that. And we like trees because sometimes, well, trees are nonlinear, but trees are really great because sometimes there's no natural linear order to something, but sometimes the data might have this like nonlinear hierarchical structure to it. An example of this might be like your file system on your computer, right? I go here, let's go C, and then under C we see all these, okay, program files, and under program file, you know, it's like this tree structure. So you've all seen, or you've all, like tables of contents of a book are like in a tree structure too. This page right here is in a tree structure. We have the topic name trees, and then we have this subcategory called like definitions and terminology. And then under that, I have another subcategory, tree definitions, nodes, relationships. So properties, I could draw all of this as a tree. The data is organized in some hierarchical way. So, I mean, here's a simple one, you know, root directory of C. Then we've got documents and settings, program files, and my music. What do I have? I've got Sigwin, eSupport, I don't even know what that is. Perf logs, I don't have permissions, okay. Program files, users, Windows, and then in all of these I have subfolders that have subfolders that have subfolders that have subfolders. These are folders full of folders, full of folders, full of folders, and so on and so on. Blech. So hopefully you get the idea. Did I hear a boop? Okay. I like learning about the logic behind why things work, but I don't like making the things work. So any settings menu of any kind is a tree as well. Settings menu. I'm not sure what you mean by settings menu. But like how, like if you go to settings and there's like categories, like settings, and then under there we've got all these other things. Yeah. Anything where it's like, oh, under personalization, and under that I've got colors, and under that I've got like, this is a tree structure. It's just, we're not really viewing it like on its side like a tree. We kind of have this like top-down view of where we go down and then we move back up. But yeah, there you go. And here's the thing. No, not necessarily. I'll come back to this. Okay, a tree. Okay, I'm going to warn you. This topic is going to be full of definitions. Fortunately, computer scientists tend to be pretty good with the words they use to describe things because we're too dumb to come up with fancy words. We just use words that are hopefully kind of intuitive. So, a tree. A tree is, here's a tree. And we define a tree recursively. But don't let that scare you. A tree is either empty or has a special element called the root from which descend 0 or more trees, which are subtrees. So, for example, here is the root. And below it are subtrees. And below this subtree is a subtree. And below this subtree is a subtree. I mean, a tree of size 1, if it's just one element, is a subtree. But these are all subtrees. So in this case, we'll use words now, nodes, to describe the things in the, like, these are the nodes. It's just, you can think of nodes from the link structure, except now the nodes might have multiple links from them, not just one, right? So if this is the root node, unlike a link structure where we've got head, and each node only has one next, this one has 1, 2, 3, 4. 4 children, we would say here. So nodes are a single thing here. An edge is the lines between the nodes. Okay, we call these edges. Why? Because. The root node is the special node that is the root or the origin of the tree. Any given tree can have 0 or 1 root nodes. Because an empty tree is still a tree. It's kind of weird, right? Like, you can think of the empty string. You can have a string that has nothing in it, but it's still a string, right? You can have a binary, you can have an empty queue. It's a queue, but there's nothing in it, right? So it's the same idea here with a tree. So the root node is the thing at the very top of the tree, but notice that, like, these are subtrees. So the root node of this subtree is this, right here. The root node of this subtree is this one. So even though a tree has 1 or 0 roots, the tree has multiple subtrees that have subtrees that have subtrees that have subtrees that will also have roots. Or maybe not if they're empty, for example. Like this one here has a subtree, well, that's empty, that's nothing. Leaf nodes, these are the ones that are just at the bottom that have no like descendants or children or things coming off of it. Because there's like a directionality here. This is the top, and then we go down. So this one here, these are the leaves. It's weird. Computer scientists always joke that, yeah, we're the weird ones where our roots are on the top of the trees and the leaves are on the bottom. Deal with it. Interior nodes, they're the ones that are not leaves. An empty tree with no nodes or edges. An empty tree is a tree with no nodes or edges. But with the definition of a tree we're using, this is still a tree. Yeah, just think of a stack, queue, bag. They still exist, but they might be empty. Okay, warning. Warning. This is a big one. Are you all listening? Warning. There are other definitions of trees. You can go and find slight variations of a definition of a tree. This is the definition we have here. And you can go find slightly different variations. They're going to be very, very similar, but slightly different. So if you're going and doing some reading on your own and you're like, wait a minute, Dr. Hughes said it was a little bit. Yeah, because you can find slightly different definitions. This is the definition that's very common, and this is the definition we're going with. But I'm giving you the warning that you might come across some that you don't, something that looks a little funny. So here we go. We've got labeled root. These are interior nodes. These are leaves. There you go. Now, relationships, so relative terms. A parent or predecessor of a given node is a node directly above in the hierarchy. So this node right here, can you all see my cursor reasonably well? Yeah, okay. So this node here, its parent would be this one right here. Why? Well, because, you know, it's like parent. A child would be like, well, this one has 2 children. 1, 2. Okay? This root has 4 children. 1, 2, 3, 4. Siblings, well, these would be siblings right here. They have the same parent. An ancestor is someone that is above. So this node right here has an ancestor that's this one, their parent, and this one. The root is also their ancestor. And in any given tree, the root will be an ancestor, like assuming it exists. It will be an ancestor to everything. So this one's ancestors are this one, and this one. But not this one. That's not an ancestor. It's like an uncle. And then a descendant is the opposite. All nodes are a descendant of the root. This one right here, its descendants are this one, and this one. I will say these two are probably the most common that you'll come across. These are all valid words, but these ones right here are the most common ones you're going to come across. And hopefully you found this terminology somewhat intuitive. Okay, can a leaf node, here's a quiz. Everyone get ready to type in the chat. Can a leaf node have any children? No is the correct answer, because a leaf node is one that has no children. So by definition, it can't be a leaf node if it has children. Does the root have a parent? No, correct. How many parents does each node have? Ooh, how many parents does each node have? 1. It can have 1 or 0 if you're the root, I suppose. Good. A subtree. Okay, I guess here we're popping up. Okay, a subtree of a given node is a child node and all its descendants. So a subtree is itself a tree, and a node may have many subtrees. So the root has 4 subtrees. 1, 2, 3, 4. Now these 2 subtrees in the middle only have one thing in it. It's a very boring tree, I guess. But the far left and the far right subtrees are quite clearly trees. And then this one right here has 3 subtrees. This one, and this one. It's subtrees all the way down until we get to nothing. Subtrees of E are labeled 1, 2, 3. Great. What is the root of the subtree labeled E? Kind of I feel like this is a dumb question. It's kind of a dumb question because it's saying subtrees of the node labeled E. This is the node labeled E. These are the 3 subtrees. And it's saying, what's the root of the subtree labeled E? Well, the subtree isn't labeled. The node's labeled. So I guess if we want to say the whole tree that starts at, what's the root of the subtree labeled E? Well, I think what I would say is the E is the root. But the whole subtree's parent is the root, I guess, here. How many subtrees does this tree have? 1, 2, 3. Is another PR? You could, I guess, if you worded it right. There's nothing. It's not terrible the way it is. I don't know. Is a leaf node a subtree? Yes. And here's the thing. By definition, a tree could be empty. So this subtree right here, this far right subtree, the little black single node there, it has subtrees. It's just they're all empty. Which is weird, right? But, I mean, it's true. Because an empty tree is still a tree. But that's like an edge case that we're talking about here. Okay, properties. A path is a sequence of nodes and edges leading from one to another. Okay, a path length is the number of edges in the path. Everyone say out loud, the path length is the number of edges in the path, not nodes, edges. And this is always a funny one because people are always like, well, if I'm looking for the path between, let's say, what's going on? Weird. Whoa. If I'm looking for the path between the root and this one, well, the path is like, okay, this, right? Here, 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 here. But the number, the length is the number of edges. 1, 2, 3. So even though there's 4 nodes in the path, the length is 3. And the way you can remember it is, what's the path between the root and the root? What's the length of that path? 0, right? What's the length of the path between the root and one of its children? Well, 1. So a path from something to itself has length 0. So you only have length until you start taking steps away. That's what the Huffman code uses. It's like the number of lines. Edges, yeah, it's the number of lines, exactly. It's the number of steps. We start here, we go 1, 2, 3, which is also the number of edges, lines, as you said. The level, okay, pay attention. The level of a given node is the number of edges between the root and the node. Or if you prefer a recursive definition, the level of the root is 0, and the level of a node that is not the root is the level of its parent plus 1. In other words, this is level 0. Wait, do I have it? I think I have a picture. Yeah, here we go. Level 0, level 1, level 2, level 3. Note that the root is at level 0. The height of a tree is the number of levels it has. Path length versus level. We're on it right now. That's not a stupid question. That is a very good question because the length, a path length and the level are very related to one another. So very good question. What? Okay. The height of a tree is the number of levels the tree has. So the level is the number of edges between the root and the node. So the path length between the root and the node. The height of a tree is the number of levels it has. So this tree here has 1, 2, 3, 0, 1, 2, 3 levels. This one. This is a different one than this one. So I would say the height of this tree is 3. And you might say, yeah, but only one of its things goes down to 3. You're right. It's the maximum one. The deepest path is the height of the tree. So here's quiz time. What is the length of the path between the circled nodes? Everyone type in the chat. No, it's 3. It's 3. 1, 2, 3. See, there's 1, 2, 3 edges. Well, that should be an easy one. Oh, from them. Oh, okay. Oh, from the 1 and 2. I see what you were saying. What is the height of this tree? 3. Good. What is the height of the tree? What is the height of a tree with only a root? Now here's a weird one. This is a really weird one. But listen to our just if you keep our definition in mind, you might be able to kind of guess. What is the height of an empty tree? -1 is correct. No, because, yeah, -1 is the right answer. And if you're like, what? Just go with it, okay? You were joking. Nope, -1 is the correct answer. 0 is a reasonable guess, but the height of a tree with only a root is 0. So what's less than 0? -1. So really, maybe I should maybe if we go back to the recursive definition, we should say the level of an empty tree, or pardon me, the height of an empty tree, or the level, no, because it's about the height though. Yeah, I guess that won't quite work, but that's okay. It is -1. Just go with me on that, okay? Okay. The degree/arity, I'm almost always going to use the word degree. So the degree of a given node is the number of children the node has. You don't include the number of parents. So what is the degree of the root node in this tree? 3. What is the degree of this one right here? It's 2. What's the degree of this one? And what's the degree of this one? Good. Very, very, very good. You don't count the parents. And the reason I'm emphasizing this is because there is a generalization of trees called graphs. And a graph, in a graph, there's no such thing as a parent or a child. So you count all edges, where in trees, you count all the edges that aren't the one to the parent. And then, of course, the degree of a tree is the maximum, is the maximum of all of the degrees in the tree. So here it's like, well, the node with the highest degree is 3. So this tree here has a degree of 3. What is the degree of this tree? We already did that. What is the smallest degree of a node in this tree? We already did 0. We already did that. Great. That's trees. Any questions about trees? At this point, it was just definitions. And at this point, it's going to get simpler because we're only going to be talking about binary trees. And a binary tree is one where it's degree 2. Okay? So any questions about the trees? If you didn't realize, the next couple topics are all about trees. We've got trees, binary search trees, linked binary search trees. So we got a lot of trees to talk about, but that's okay. Any questions about trees? I'm not seeing any, so that's cool. What one do we use for assignment 4? None of them. Although it's going to be I think it would technically be a binary tree, right? I mean, yeah, but it's still a tree. It's just you're making a Huffman tree. Yeah. Maybe it was a semantics issue there. All right, let's move on. So a general tree is one where each node can have any number of children. So a tree is just something that looks like what we were talking about. An n-ary tree, so in this case, a binary tree, because it's 2. A binary tree is one where each node has no more than n children. Here, 2 children. So here's a binary tree, right here. Ignore the letters for now. Those labels are going to be there for ease later. Each node has at most 2 children. The root has 2, B has 2, D only has 1, but that's okay. It just can't have more than 2. H has 0, E has 0, I has 0, F has 1, C has 2, G has none. There we go. A binary tree is one where each node has no more than 2 children. So here, I could also say, oh, this is a tree with degree or arity of 2. Yeah, so it's a degree 2 tree. Almost every human on this planet would call this a binary tree, though. If a node has children, they're referred to as left and right. Okay? So that means that, like, a general tree just has children, where a binary tree has a left and right child. So there is some amount of, like, directionality now, where it kind of means something to be the left or the right. Where a general tree just has a bunch of children. It could just be like a set of children where there's no order or any meaning to which one comes when, where here we have left and right. So we now kind of have this sense of, like, direction or order here, but more on that to come. So if A node has children, they're referred to left or right. So which are referred to as left and right subtrees? Yes. Okay. In the above example, B is the left subtree of C and A is the right. Wait. Oh, B is the left subtree and C is the right subtree of A. So A has a left child of B and a right child of C, which of course A's left right child, B, is also the root of this whole subtree, right? So A's left child is also the root of a subtree. C, A's right child, is also the root of the right subtree, okay? In a binary tree, position matters. It matters if a subtree is left or right. Now, a recursive definition of a binary tree is an empty tree, or a tree that has a root whose left and right subtrees are also binary trees. So if we go and compare this to the definition of the general tree, you would see it's nearly identical. It's just here we've got the limitation of 2, where, here we have a limitation of 2 with left and right, where with a general tree, it's just got like 0 or many subtrees. Okay? So far, so good. Now, here's a little quiz for you. Based on all of this information we just saw, what would a unary tree look like? Curious. It's a test. A binary tree has 2. What's a unary tree? A root? Not quite. A line. A straight line. Yeah, it would be. It would be like a linked bag. Right? Where it's, oh, okay. It would be like a simple linked structure. Right? Because like, oh, each one only has one child. Oh, so a next. All right. Traversals. So the big thing we're going to be talking about here are the traversals. Let me make sure I'm correct about that. In order, interface. Yeah, okay. And then we get to the interface of it. Okay, cool. Now, a traversal. When we had simple linear data structures, the order that you traverse the thing is obvious, right? Here's a linear data structure. Here's a unary tree. Okay, you start at the beginning. What comes next? The next thing. If you have an array and you start at index 0, what comes next? Index 1. Why? Because, I mean, that you can't even, because that's the way it is. It's because what comes next? There is a single next. If I show you this though, and I say, okay, A, what comes after A? You go, well, it's either B or C, I guess. Yeah, I don't know. Because we have a choice to make. What comes next? Maybe left. You know, we read left to right, so I guess left makes sense. Okay, I guess there's some reasoning there, but it would also be natural to maybe go to the other. Like, I don't know. It seems kind of arbitrary to say left, where here, when I start at the beginning of a link structure and I say go to the next thing, I'm not making an arbitrary decision. It's like, okay, well, what's the next thing? Where here, it's what's the next thing? I've got a choice to make. The next is, yeah, it's B and C, but which one? If I need one, what's the next one? So with nonlinear data structures like binary trees, the order of the traversal, the order to traverse the nodes in is not immediately obvious. So we have a few common options, and we're going to talk about 4. Pre-order, in-order, post-order, level order. Pre, in, and post are going to be remarkably similar in algorithm, but will appear a little different in terms of like what we get, but the algorithms are going to be hilariously similar. So a pre-order traversal, okay? It's one of the common traversals of a binary tree, or any tree really, but we're talking about binary trees. So the general idea is start at the root, access the node, get the data from the node, then go to the left child, then go to the right child. That's the process. But remember, the left child and the right child are also roots of their own subtrees. meaning we would be starting at the root again. So to get more precise, I could say a preorder traversal is if the tree, subtree, is not empty, access the root of the subtree or tree, do another preorder traversal on the left subtree, and then do a preorder traversal on the right subtree. That's the idea right there. So, and note that the root of the subtree is accessed before any recursive calls. So we access the root before or pre, if you will, any recursive call. So here's how I would do it. We're going to follow this. Access the root. Okay, access the root, I get A. I'm going to copy. Paint. That is not paint. That's ain't. Paint. Okay. Nope. I wish I could do like 150, but that's okay. Hopefully y'all can see this pretty well. So I start at the root and I access the data. Okay, I see A. Then I go to the left. Boom, done. Okay, great. I'm now at the left, but hey, wait a minute. I'm doing a preorder traversal on this subtree. So I access the root, which is B. Then I go to the left. Okay, great. Oh, I'm doing a preorder traversal on this node. So I access the root of that subtree, which is D, and then I go to the left. And then I go to the left and I go, well, okay, there's nothing there, so I don't have to print anything. And so I'm done, and I go back to here. So now I'm back at D. So I printed out D. I dealt with D's left child, which was nothing. Now I just deal with D's right child, because the order is node, left, right. So we did node, we did left, which was nothing. Now we go to the right. So go to H. Okay, we access the node, H. We go to the left, nothing there, return. Go to the right, nothing there, return. And now we're done with H. So we return to D. Great. We just finished D's right subtree, meaning we're done. So we return to B. Now we finished B's left subtree, so we do a preorder on the right subtree. Okay, go to the E, access the E. Go to E's left, nothing there. Go to E's right, nothing there. We're done with the E, return to B. We just finished B, return to A. Oh, so now we finished A's left subtree. So we did all of the preorder traversal on the left subtree. Now we just need to do a preorder traversal on the right subtree. So we go to the C, access the C. Go to the left, access the left. Go to the left, access the left. Go to the left, nothing there. Go to the right, nothing there. We return. We finished I. We finished F's left subtree. So now we do F's right subtree. Nothing there. Return. Now we're done with F. Return. We finished C's all left subtree. So now we go to C's right. We get G. Go to G's left. Nothing there. Go to G's right. Nothing there. So we're finished with G. We return to C. We finished with C. Return to A. And because we just finished C, which is the right subtree, we're done with A. Huh. That's the preorder traversal. A, B, D, H, E, C, F, I, G. Or 6, because I can't draw a G. That's worse. Anyways, we'll end here. And we'll pick up here, I guess, Friday.